And we're going to count down. All right, it's time to start, folks. Count down here, 5, 4, 3, 2, 1. Correct choices are copper and molybdenum. And how do we know it's to look for copper and molybdenum? What are we looking for?
The ones that end with D10, D something.
Ones that end with D something.
D10 and D5.
Right, D10 and D5. These are ones, we don't know the explanation entirely for sure, but it seems to be that the atom has tends to have a bit lower energy when they have the D5 or D10 arrangement versus the almost filled or almost half-filled orbitals. All right, I guess it's filled or almost half-filled subshells, not orbitals. Okay, next up, there are some figures that we're going to look at in your text, and I don't know that I have page references for these. I guess I do. Page 353, and we'll be looking at a few of these figures here today, and I do have some that we can look at up here. And I'm showing page 353, but here it's 348. I guess it's page 348. Or am I the wrong day? No, this is the right day. Here we go. Page 353. Here we go. So what this is a plot of is a plot of the atomic radius versus the atomic number. So again, this is a plot of the atomic radius versus the atomic number. So the radius is on the y-axis, atomic number here on the x-axis. And what we're starting to look at here today is an examination of what we call periodic trends. Periodic trends. And periodic trends basically is an explanation to some of the repetitive behavior that we see amongst the elements on the periodic table. And I'm guessing we're probably going to write on the periodic tables a lot today, so it probably doesn't hurt to have another copy. I don't even need to say that. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. And I'll get one up here myself. So what I'd like for you to do now is to look at the periodic table, and then let's look at this data trend. And the first trend we're looking at of probably 3 different trends, maybe 4 different sets of trends today, is atomic radius. And I don't have any individual, well, sure. I suppose I can pull out one of these here and just use this to represent an atom. We're talking about the radius. What is the radius of a sphere? It's the distance from the center to the outside. Okay, so when we look at the radius, we're talking about what that distance is from the center of the atom, that is the nucleus, out to the outer edge of the electron cloud. And so this shows what those trends would be. So what I'd like for you to do now is to examine those trends and then go to your Socrative app and answer the questions here. And that is, what are the general trends for the atomic radii in the periodic table? Select all of the answers that apply. And I'll show the trends here once again. Take a look at the data. If you don't have your textbook open yourself. Talk with a neighbor before you commit yourself. What are the general trends? Now, if it helps to look at it this way, here's another way that we might represent the data. like to look at it this way. And look at it this way. All right, let's get your answers locked in, please. Let's get your answers locked in. And we're going to count down. 5, 4, 3, 2, 1. Now, of course, I realized once I showed you the second one that it actually gave the answers to you. But as we go across from left to right, now what's the first one there? Within a group. So as we go down within a group, this is one that follows our general trends. And if we go back and look at the diagram, that is, as we go down within a group, like this, we see that the radii tend to increase.
Oh, I missed that.
Yeah, gave away the answer.
Literally right there.
Exactly. And as we go across then from left to right, then the radii tend to decrease. So again, they tend to decrease as we go across from left to right. Now, which one of these two, just from the onset, makes the most sense? One of these trends should make sense. One of the trends shouldn't make sense. Which one does make sense? Right. As we go down within the group, the radii increase. And of course, that one is explained very easily because as we go down within the group, what's happening to the number of energy levels? Increasing. So as we add on energy levels, then we would expect the radii to increase. The one that probably doesn't make sense, though, is the one that we observe when we go across from left to right, because as we're going across from left to right, what is happening to the number of electrons? It's increasing. And because it's increasing, we may expect that the radius should increase as well, because after all, if we're putting more electrons into the cloud, what do light charges do? They repel. So with more electrons in there, we may expect to see an increase in repulsions, an increase in size, and we don't observe that. Now, the reason why we don't observe that, the explanation lies in what we call the effective nuclear charge. It's called the effective nuclear charge. And we define the effective nuclear charge like this. We define the effective nuclear charge as being the nuclear charge that is experienced by the valence electrons. And what's key to it here is this word effective. It is the nuclear charge experienced by the valence electrons. Now the example that's given here is lithium. And in the case of lithium, lithium has how many protons in its nucleus? 3. And where do we get the 3 protons from? Atomic number, exactly. If we come back to lithium and look at its periodic table, to its atomic number, we see the atomic number here is 3. Because it has atomic number of 3, then we see the 3 protons in the nucleus. We would also say that the nuclear charge in this case is 3 positive. Okay, now, the effective nuclear charge, though, is examined something like this. If you recall the electron configuration for lithium, the electron configuration for lithium is 1s2, 2s1. And what this means is that there's 2 electrons that are in an inner level, which we also refer to as the core electrons, and then we have 1 valence electron. So since we define the effective nuclear charge as the nuclear charge experienced by the valence electrons, we calculate it or approximate it something like this. Basically, the nuclear charge being 3 positive is going to be canceled out by the 2 inner level electrons. So again, the nucleus here, the charge in the nucleus will in effect be canceled out by whatever inner level electrons we have. So in the case of lithium, how many inner level electrons are there? There's 2. And since there's 2 inner level electrons, they in effect cancel out the effect of 2 protons. And in effect then, we're left with the effective nuclear charge of 1 plus. So now if we were to diagram this and kind of go across, we're going to make a diagram of this and we'll look at what that effective nuclear charge might look like. We'll start with something like lithium, which again we see here has the 3 protons in the nucleus. And then we'll just kind of simplify it. We'll show the 2 inner level electrons, and then we'll show the valence electron. And again, this is for lithium, which has an electron configuration of 1s2, 2s1. And so again, we're looking at this outer level electron, which is the valence electron, and that valence electron is having the nucleus, or the nuclear charge, basically being canceled out by 2 of the electrons. And so the way that we label it is like this. Z represents the nuclear charge, and if we give it a subscript like this, this represents the effective nuclear charge. We would say in the case of lithium, we would approximate it to be about 1 plus. Because again, we have the 3 protons in effect being canceled out by 2 electrons. If we went on to something like nitrogen, and then we're going to look at neon. If we write out the electron configurations for these 2, for nitrogen, we would write it out as 1s2. Let's see, here's nitrogen. That's going to be 1s2 followed by 2s2. And the configuration of nitrogen should end with 2p3. Remember, this is p1, p2, p3. And then we're in the N block, or the P block, we say it has an NP configuration. So it's going to end with 2p3. And if we're dealing with neon, the configuration would be 1s2, 2s2, and would end with 2p6, like this right here. So then if we wrote out their diagrams, it would be kind of like we'd say that it's Bohr model. How many protons would nitrogen have in its nucleus? 7. Neon would have 10 protons in its nucleus. We then show the different levels. There's 2 levels in each one, the first and the second. In the case of nitrogen, how many electrons go into the first level? 2. How many go into the second level? Not 2.
5.
There's going to be 5. These are all a part of the second level. So we put in 1, 2, 3, 4, 5. And in the case of neon, how many inner level electrons would there be?
2.
2. And how many outer level electrons would there be?
6.
I hear 6, I hear 8. What is it?
8.
It's 8. So we put in 1, 2, 3, 4, 5, 6, 7, 8. In case you're wondering where that's coming from, we have a total of 8 electrons in the second energy level. So now if we want to approximate the effective nuclear charge, remember the effective nuclear charge is the nuclear charge experienced by a valence electron. It doesn't matter which one we pick, just pick a valence electron. And if we look at a valence electron here, a valence electron right here, the nuclear charge it sees is going to be canceled out by how many inner level electrons? Just 2. And a valence electron here is going to be canceled out by how many inner level electrons? Just 2. So you see then what happens is that when we go and determine the effective nuclear charge here, since this nucleus is being canceled out by only 2 inner level electrons, the effective nuclear charge experienced by a valence electron in this case would be about 5 plus. And in the case of neon, the effective nuclear charge here would be approximately 8 plus. And again, we get that based on the fact that we have 10 protons in the nucleus and in effect being canceled out by 2 inner level electrons. Now those inner level electrons are referred to as either core electrons or shielding electrons. So the inner level electrons are also called core electrons or shielding electrons. And we have these names in the case that we'd say that they're core electrons because they're part of that inner core. We also call them shielding electrons because they in effect are shielding the valence electrons from the nucleus. So again, those inner level electrons are called shielding electrons because they in effect shield the valence electrons from the full effect of the nucleus. But what we can see happens here as we go across from left to right in the periodic table, what happens to the effective nuclear charge? It increases. And so as we go from left to right, the effective nuclear charge increases. But what happens to the number of energy levels? They stay the same. So going across from left to right, we still are only having 2 energy levels, but the effective nuclear charge increases as we go across from left to right. So the net effect is that, remember that opposites will attract. They tend to pull that cloud in closer to the nucleus. And as a result then, the trend that we wind up observing is something like this, and that is that the radius decreases as you go across from left to right. Now again, it's not a perfect trend. Notice that there are some exceptions once we get in here. And once we get down here, it does not decrease a whole lot. In fact, it goes up and down a little bit. But as a general rule, it still decreases as we go across from left to right. And part of the reason why it does not decrease so much more once we get into here is that, remember, not only are we increasing the effective nuclear charge, but because we're packing more electrons into the same energy level, we also have the effect of repulsions taking place. And so those repulsions kind of counteract the effective nuclear charge and tend to push things back out. So again, the main explanation we use as they go across from left to right is that the effective nuclear charge increases, but we also have the competing repulsions that take place from simply packing more electrons into a given energy level, which have some repulsions. So any questions on that general trend? Any questions on the general trend? Okay, by the way, as I'm going through there, these are an approximation of the effective nuclear charge. They are not an exact calculation. If you go on and take a course in physical chemistry or inorganic chemistry, you'll learn a much more precise way of calculating them. This would be a good enough approximation to get the explanation that we want. Let's go ahead and calculate the effective nuclear charge of arsenic. Not argon, but arsenic. Let's determine what that effective nuclear charge is. And this will be the next question on your Socrative app. What is the approximate effective nuclear charge experienced by a valence electron in an atom of arsenic? So once again, I'll get you started, but you're going to do the calculation yourself. You're going to start by writing out the electron configuration. Then you're going to draw the nucleus. Then you're going to show the number of energy levels in there. And remember that whatever the number of energy levels is, you want to subtract out all of the inner level electrons that would cancel out the effect of the nucleus. So for arsenic. And before you commit yourself to an answer, check with at least a neighbor or two to make sure you're on the same page. And again, your question is, what is the approximate effective nuclear charge experienced by valence electrons in an atom of arsenic. So we'll start by writing out the configuration. See how we're doing here. Commit to an answer. Give you about 1 more minute.
Okay, if that makes sense to do it that way. That's where I'm sitting at.
All right, let's get your answers locked in here, please. We'll count down. 5, 4, 3, 2, 1. Correct answer is 5 plus. 5 plus. Now, you would get it something like this. You'd write out its electron configuration, and we would see we have a total of how many valence electrons? How many valence electrons? There's 5. If you counted through there at the number of electrons in each level, how many are in the first energy level? 2. In the second there'd be 8. In the third there'd be 18. And in the fourth one there would be 5. So all together, if you sum together 2, 8, and 18, you would get 28. You then subtract that 28 from 33, and you'd wind up with the effective nuclear charge of 5 plus. Any questions? All right. Next up, we have some trends in first ionization energies. And here's what the first ionization energy is. First of all, we'll talk about what the word ionization energy means. And the ionization energy is defined like this. We say that it is the energy required to remove an electron from an atom or ion in the gaseous state. It's the energy required to remove an electron from an atom or ion in the gaseous state. Now, I don't have the page reference for this, but here's what that would look like. And this is for what's called the first ionization energy. We have the first ionization energy. We can have second, third, fourth, and fifth ionization energies. The way that we sometimes label them is like this, IE with the subscript 1, so we call IE1, IE2, IE3, IE4, and so forth. As we go across then, on this particular table, we said this is the first ionization energy, this is the second ionization energy, third ionization energy, fourth ionization energy, and so forth. And so the first ionization energy would be the energy required to remove the first electron. The second ionization energy would be the energy required to remove the second electron from an atom. The third ionization energy would be the energy required to remove the third electron from an atom, and so forth. So I have some questions for you that I'd like for you to answer, and I'm going to kind of scroll through this data, and some of this is going to come up, at least one of them here, in your Socrative app. But here are the questions that would like for you to think about. And I'll put this right here, and I'll see if I can type these out. So the first one is this. Let's see if I can put it in here. What are the general trends for the first ionization energy in the periodic table? So that would be the first question. Second question would be, there we go, how do these trends compare to the atomic radii? So again, how do these trends, how do these trends compare to the trends for atomic radii? That would be question number 2. Question number 3 would read like this. Explain the values of successive ionization energies Explain what the values, I forgot a word there, explain why the values of the successive ionization energies increase with each electron. All right, and then the last one here would be explain why there is such a large jump from one side of the staircase to the other. And this would be, if you can see colors, from blue to pink. All right. And I'll show you what each one of these are. So these are the questions I'd like for you to answer here. And as far as the diagrams go now, let's look at the diagrams. Here's what the table for the first ionization energies look like. So take a look at the first question, analyze the data, talk with a neighbor here, see if you can answer your first question, which is, what are the trends? And I guess the second question is, how do these trends compare to the atomic radii? So these are your first two questions. And then that question will show up on the Socrative app. First question will show up on the Socrative app. Okay, let's get your answers locked in, please. I'll give you one more peek at the trends. All right, let's check out the answers. Count down, 5, 4, 3, 2, 1. All right, they decrease as they go down within a group, and they increase as you go across the period from left to right. And how does this compare to the atomic radii? Just the opposite, exactly. And we use the same explanation as we did with the atomic radii. And that is, if we looked at the size of the atoms, as the electrons are drawn in closer to the nucleus, remember that opposites will attract each other. So then that means that the energy required to remove an electron is going to be greater the closer it is pulled into the nucleus. It's just kind of like if we had a couple magnets. If you've ever played around with magnets before, when is it the hardest, or which position is it the hardest to remove them from each other? When they're closer together, exactly. So if they're already starting further apart, it's going to be easier to pull those electrons out. So electrons that start further away from the nucleus are going to be ones that are going to be more easily removed. Okay? Any questions on that? Now, what do you need to know? Everything. Okay? You need to know what the trends are, but you also need to know the explanations. Okay? The explanations are simple, right? Got the explanation? Got it? All right. Because sometimes, well, what are we supposed to know from all this? Well, everything, as usual. All right. So, next question was, explain why the values of the successive ionization energies increase with each electron, and explain why there's such a large jump from one side of the staircase to the other. Now, that's referring to this diagram right here. So, take a look at the elements now, and locate the elements on the periodic table. And remember now that the IE1 is the energy required to remove the first electron, i.e. 2 is the energy required to remove the second electron, and so on. And then pay particular attention to the big jump here as we go from the blue side of the staircase to the pink side. So I'll give you about a minute or two here. Think about it, write down your answers, or talk with a neighbor. See why you think we can explain those. Go ahead. All right. Who cares to give this a shot? Let's start with the first one here. Go ahead. Mohammed?
I think it's closer to the.
Quiet, please.
I
Mohammed?
think it's closer to noble gases. It takes more ionization energy to get it closer to noble gases. Like when it reaches noble gas, it doesn't take no energy.
Okay. Probably a little bit more to that. It was talking about as we approach the noble gases, it doesn't require. Actually, as we're approaching a noble gas configuration, these energies are getting to be quite a bit more.
When it hits noble gases, it takes
Okay.
no energy.
Okay, so what you're saying, when you get to the noble gases, and you're talking about the first ionization energy, is that right?
Mm-hmm.
Okay, that is correct for the first ionization energy. What we're talking about is the successive ionization energies. So by successive, we mean going from 1 to 2 and then 2 to 3. Why do we observe, say when we go from 1 to 2 and then from 2 to 3, why do these values increase? So you were right for first ionization energies, but for the successive ones? Yeah.
Is it just because there's less electrons, so there's a greater attraction, so it's going to pull out?
Exactly. That's exactly what it is. So in the case of aluminum, if we remove one electron, we take one electron out of there, then remember there's now more protons than there are electrons, so if we take one electron out, what is that going to do to the electron cloud? It's going to shrink it down. We take out a second electron, what is that going to do? Shrink it more. We go to aluminum, we take out the third valence electron, what is that going to do? Shrink it down even more. But in the case of aluminum, the next thing that happens in aluminum, if we wrote out the electron configuration for aluminum, it's going to be 1s2, 2s2, 2p6, 3s2, and 3p1. This is for aluminum. So why then the big jump when we go to the fourth electron? Go ahead, Jacob.
Because when you take all of the electrons out of the valence shell of an electron, then the next layer down becomes sort of a pseudo-valence shell, and the effective nuclear charge is massively increased.
Yes, it's going to be massively increased, exactly. So basically what we've done here is we've removed an entire valence shell, and if you want to call it a pseudo-valence shell, whatever, it's basically a new valence shell that we have, and we've removed an entire, like a layer of an onion there, and that effective nuclear charge increases dramatically once that valence shell is removed. So we see the huge jump then in these successive energy levels when we go from this blue area to the pink area, because the blue area is just a point where we pull out the last valence electron. And at that point then we have a new valence shell. This pink side over here represents these core electrons, or that new valence shell that form once we've removed enough of those electrons out of there. So, very good. Any questions with these? All right, then the next table and pattern we're going to look at. Oh, and I think probably it'd be helpful if you want to kind of put these all onto a periodic table, just kind of trace out their trends. What I would do is something like this, just to remind myself. We look at the atomic radii as a general trend. Again, what happens as we go across from left to right? It'll decrease. And as we go down within a group, the radii will increase. And then if we look at the first ionization energies, as we go across, the first ionization energies will increase. And as we go down within a group, the general trend is that the values will decrease. And the key to it all is to learn the atomic radii and the explanation. If you learn the radii and explanation, remember that the first ionization energies are just the opposite of the trends for the radii. The last set of periodic trends we'll look at here are what we call the electron affinities. And we define the electron affinities like this. The electron affinity we define this being the energy change associated with the addition of an electron to an atom in the gaseous phase. Now the electron affinities, if we looked at these values, there are no real general trends to these, other than we see that these elements here of group 7A, elements of group 6A, these have a very high electron affinity. And basically that means, if we talk about what the word affinity means an attraction for electrons. And so when we have large values here, like we do over in group 6A and 7A, these have a high affinity or a high attraction for electrons. But if we try to come up with general trends as we go, say, down within a group or across from left to right, we don't have the same really nice predictable trends for these as we do for the other properties. Any questions with these? Okay, next we're going to look at ions. We're going to move on from neutral atoms to ions. And let's write out electron configurations for these ions. We have the sodium ion and the oxide ion. Now, writing out the electron configuration for ions is different than writing them out for neutral atoms. If we're going to write them out for the ions, we always start as a beginning point of writing it out for the neutral atoms. So let's start, and we write out complete configurations for these. So let's write out a complete configuration for sodium. We'll have 1s2, 2s2, and we need to get up to 11 electrons. So that means we'll go then to 2p6 followed by 3s1. And if we went to oxygen and wrote out its configuration sitting right here, we need to get up to 8 electrons. So we'll put in 1s2, 2s2, and 2p4. Now these are for the neutral atoms. And hopefully you're writing in pencil. Okay? Because now, if we want to write out the configuration for the ions, let's go to the sodium ion and go to the oxide ion. What does it mean if we have a positive charge? Have we gained or lost electrons? We've lost electrons. That means we lose one electron, and this becomes the electron configuration for the sodium ion. So rewriting it, we'd have 1s2, 2s2, 2p6. And if we go to the oxide ion, a charge of 2 negative means what? It's gain 2. So we've gone from 2p4 to 2p6. So we write out that configuration as 1s2, 2s2, 2p6. How do the electron configurations compare between these two? They are the same. Okay, their electron configurations are the same. We say that these two are isoelectronic. They are isoelectronic, and we sometimes describe them by saying that they are isoelectronic species. And that means that they have the same number of electrons, the same electron configuration. So now, here's what I'd like for you to do with these. First of all, let's determine the effective nuclear charge on these ions. So find the effective nuclear charge of the sodium ion, find the effective nuclear charge. And when I say the effective nuclear charge, this would be the effective nuclear charge experienced by valence electrons in each one of these. So find the effective nuclear charge experienced by the valence electrons for each one of these. And remember now that these are the valence electrons for the sodium ion. These are the valence electrons for the oxide ion. And of course, once you do that, we have questions on the Socrative app. What is the approximate effective nuclear charge experienced by valence electrons in a sodium ion? And then the effective nuclear charge experienced by valence electrons in the oxide ion. So remember, if you need to, draw out your diagram. Talk with a neighbor before you commit yourself to an answer, that is. All right, let's get your answers locked in, please. And we will count down. 5, 4, 3, 2, 1. We're going to do this one without explanation. Before we look at the second one, 9 plus is the correct answer. If you didn't get it right, talk with a neighbor to see why you didn't. I'll give you about 30 seconds here to talk with a neighbor. If you didn't get it right, talk to somebody that did get it right. Then use what you learned to answer the next one. Use what you learned to answer the next one. What is the approximate effective nuclear charge experienced by valence electrons in an oxide ion? And we'll count down. 5, 4, 3, 2, 1. All right, much better on this one. 6 plus. You check out your answers. Here's how we arrive at them. Okay? 11 protons in the sodium ion, 8 protons in the oxide ion. We look at a valence electron. Valence electron here is going to be shielded by 2 inner level electrons. That's the 1s2. We take 11 minus 2, we get 9 plus. In the oxide ion, we have 8 protons in the nucleus. We have 2 inner level electrons. So that will cancel out the effect of 2 of them. 8 minus 2 gives us 6 plus. So now look at these carefully. Study these two. Then the next question is going to be, and don't blurt this out, you can talk with a neighbor. If I then asked you which of these two ions is larger, which one would have a larger radius? Think about which one would have a larger radius and why. Then answer the next question. And it should say which one is expected to have the largest radius. So that's what it means. So which one do you think would have the largest radius? So we'll count down on this. We'll give you about, I won't count down yet. We'll give you about 30 more seconds. And we'll count down. 5, 4, 3, 2, 1. All right, oxide ion. All right, which one is the largest? Oxide is the largest. Now if we come back to this and look at the reason why it should be the largest, again, oxide is going to be the largest one. And those that got it right, why would this one here be larger than the sodium ion? Go ahead, Don.
Because with sodium ion you have more protons than electrons, so the electrons are attracted and are close to 2 protons, whereas that one is like, has an effective of 6, but on the outside it's 8, so you have the 6 and 6, and there's like 2 left that are like farther away, so the radius is bigger.
Exactly. So again, if you're comparing effective nuclear charge, again, which one of these is going to have a greater pull on the electron clouds? Yeah, the 9 plus here is going to have a greater pull on the electron cloud. And the size of the electron cloud, each one of them has how many electrons? There's 8 electrons. So if we have a 9 plus pulling on 8 electrons or a 6 plus pulling on 8 electrons, the one that's going to have the greatest effect is going to be the 9 plus. And so that's going to shrink it up. This one here is going to be a smaller ion than this one over here. So now, you look at this model. this here is if we were to go and look at sodium chloride and to, let's pull it over here, a little bit too much talking and stuff, all right? If we were to look at this model now, this represents sodium chloride. Which one of these would be sodium ions, and which one of these would be chloride ions? Chloride is the bigger one, sodium ions are the smaller one. And now, that's always going to be the case when you look at positive ions and negative ions, because positive ions, like the case of sodium, will have lost electrons, so the electron clouds are going to shrink a whole lot. And then your negative ions are always going to be your large ones, because if they've gained electrons, now you're going to have more repulsions, and those repulsions are going to push those electron clouds out. So moving on into your text here, we have the radii of atoms versus their cations and atoms versus their anions. And so if we looked at something like sodium as an example, this here on the left-hand side represents the neutral atom. On the right-hand side represents the size of the ion. And you can see that a sodium ion is much smaller than a sodium atom because it has basically lost an entire valence shell. So again, when we went from neutral sodium here with the valence shell with the 3s1 to this right here, we lost not only an entire valence shell, but the effective nuclear charge increased dramatically when it does so, and that serves to shrink it way down. And then if we went and looked at what happens over here on the other side with the anions, once we gain a couple of electrons, like oxygen going to the oxide ion, we now have added a couple extra valence electrons in. We've gone from a total of, in this case, 6 valence electrons, a total of 8 valence electrons. There the repulsions take over, and they serve to increase the radius. Now, I know some of you might be asking, so what? Who cares? Do I really care? I mean, some of these things here, I mean, I can't give you all the explanation of why things are important or whatever, but it might be that we're looking at trying to find a cure for cancer and try to fit atoms or something into places that have a certain size. So we might look at atomic size or the ionic size to go ahead and fit in and substitute for atoms or molecules in certain places to maybe combat a certain effect. Sometimes by simply placing in a different atom of a similar size, we can change the behavior of a certain type of molecule. Now at this point we don't have the background to deal with that, but one of the first things you'll be covering in the second semester of this course is you will be talking a bit more about crystal structure and such. And then when it comes to crystal structure, the size of the atoms that make up that substance will ultimately determine shapes of crystals and such. All right. Next up here, any questions on these that we've done here? All right. Next up, then, let's look at a couple of other electron configurations. Let's say that we look at the electron configuration of tin. And then for the tin 2 ion and the tin 4 ion. So let's write out electron configurations for each one of these. And it's easiest to start with the electron configuration for tin. So if we write out the electron configuration for tin, we are right here. So to write it out, we go back to the previous noble gas, which in this case is going to be krypton. We'll put the krypton in square brackets. And after krypton will come these two, which would be 5s2. All of these, which would be, I hear 5d and 4d. What is it? It's 4d. Remember when the d block gets the n-1 d configuration. So it'll be 4d10, and then these two, which would be 5p2. So 5s2, 4d10, 5p2. If we then went on to write out the configuration for the tin 2 ion, a charge of 2 plus means what? Lost 2 electrons. Now which 2 electrons go away?
5p's 2.
The highest energy ones, which would be the 5p. And so then this would be the configuration for the tin 2 ion. And if we went to the tin 4 ion, we need to get rid of how many more? 2 more, or 4 from neutral tin.
Yeah.
So now which ones go here? Here's how it works. When we remove electrons, the electrons that always leave first are going to be the valence electrons. And the valence electrons are the electrons that are in the outermost energy level. So in this case, it's the 5th energy level. And that might be one of the reasons why writing it in the order of increasing distance from the nucleus would be helpful. So remember that this would be another way we could have written this configuration. And writing it this way very clearly shows we have all the valence electrons together, that it's these here that go first. So go ahead then and write out the electron configuration for these ions. Let's write them out for the zinc ion, and let's write them out for the iron 2 ion and the iron 3 ion. So write out the electron configurations for these 3 ions. All right, help me out here. I don't think these are Socratic questions. So zinc 2, or the zinc ion, would be
Argon.
argon 3d10.
Yep.
Let me see if I agree. Yep, sounds good. Next up, iron 2 ion would be
3d6.
sounds good.
3d.
And iron 3 would be argon.
3d5.
Oh my gosh, you're so good. All right, here's how we're going to wrap things up today. It looks like we might get done a little early. We'll make up for the minute or two I held you over the other day. Next up, we are going to look at Lewis diagrams, Lewis symbols. And that's what the other periodic table is for. If you have room to write on the other ones, you can. And I realized and that's okay, I passed out periodic tables that I give to my 10-20 class. They have a few less elements to memorize. If you're wondering why the shading isn't quite the same, I haven't memorized about 3 or 4 elements less. Okay, but it's the same otherwise. All right, so next up we're going to look at Lewis. I'm going to write these words out. Lewis and the word electron. And in the second column, I'm going to put the word dot, and then I'll put the word figure, symbol, diagram, and structure. And the reason why I'm doing this is because you don't have to write all this down. Is because this is one of those areas where chemists haven't standardized our vocabulary. Basically, if we have the choice of taking 1 or 2 words from the first column. We can choose to take a word out of the second column and any word out of the fourth column, and any of that combination will mean the same thing. So, a Lewis figure is the same as a Lewis diagram, an electron dot diagram, or a Lewis electron dot structure, or a Lewis structure, or a Lewis dot symbol, all mean the same thing. Okay? So if you hear me use one word one time and a different word the next time, it's just because we haven't standardized our vocabulary. So, that said, what the Lewis diagram does is this, is it tells us or shows the valence electrons in an atom. And if we look at all of these here in group 1A, you remember that these all end with a configuration of S1. And as a result, they all have 1 valence electron. So the Lewis diagram, when we write the Lewis diagram, we write it with the symbol, and I'm just going to show a generic symbol now, with one dot. And the location of that dot could be anywhere. We think of it as having four sides, a top and a bottom, and a left or right. So writing it on the right-hand side would be the same as writing it on the left-hand side, which is the same as writing it on the top or writing it on the bottom. Doesn't matter. Everything in group 2A is going to have two dots or two valency electrons. Now the convention is this: when we write out the Lewis symbols, we place one dot on each side before we begin doubling up. Okay, but we could put it on any sides, top and bottom, left and right, top and right, and so forth. If we go on to group 3A, these all have three valence electrons. Okay, we have three dots. And if we go on to group 4A, we have four dots or four valence electrons. Group 5A, we have five dots or five valence electrons, and so on, until we get all the way over to group 8A, which is going to have a total of two on each side, or 8 valence electrons, with one exception. That exception is helium. In the case of helium, we write the Lewis symbol. We kind of throw out the rules about put one on each side before we double up. In helium, we double them up. We're not going to, well, we can worry about that today, sure. Worrying about it today, the first energy level can only hold up to 2 electrons. And I think probably, as we showed last class, I could go back, but the orbital diagram would show 2 electrons paired up, one spin down in that atom, so that's the 2 electrons paired up. So then, if we were to write out the Lewis symbol for something like calcium, what would the Lewis symbol for calcium look like? Ca with 2 dots. And phosphorus then would have 5 dots. The placement of the dots, again, isn't critical as long as we place one dot on each side before we double up. And because I held you over 2 minutes the other day, I'm letting you out 5 minutes early here today, because I'm a nice guy.